This is my presentation about a thermodynamic related journal, and I chose Looking for Absolute Zero Using an Arduino by F.S. Oliveira, L.B. Calhero, D.F. Bozano, N.C.G. Erobidart, M.I.A. Jardim, D.D. Rice, and A.M.B. Goncalves, presented by One Imposter Among Us. That's me. So looking for absolute zero using Arduino. I got this from a Brazil paper from the website Physics Education Journal. Let's start. So for the abstract, we presented an Arduino approach to collect pressure and temperature data from electronic sensors. Using a constant volume metal vessel immersed in a water bath and changing its temperature, we measure the pressure as a function of the temperature inside a vessel. With this apparatus, it is possible to demonstrate Gay-Lussac's law. And based on measurements of pressure and temperature, we can establish the absolute Kelvin and temperature scale. So this study wants to measure the absolute temperature through a simple experiment using this Arduino sensor. So we know that they're using a gas inside a volume metal vessel, and we know that gases are affected by quantities such as pressure, temperature, and volume, and also its number of moles. So with this, they try to utilize a specific gas law, which we will study in the next slide. For the intro, when a gas was confined in a constant volume vessel, the gas pressure P is directly proportional to the gas temperature T. This phenomenon can be represented in the ideal gas law by equation, where the N here is the number of moles of the gas and R is the ideal gas constant. Looking at this, we can see this is Gay-Lussac's law. Okay, so if you can remember, there are those gas laws that we have studied maybe in our high school or elementary years, and one of these is the Gay-Lussac's law. Let us look closely with this Gay-Lussac's law. So with this, it says that pressure is directly related to temperature. So once we know this relationship, we can use it to make a thermometer, or as they have shown in this paper, it is possible to prove such a relationship. And in the current studies, though, they found out that many authors just use sophisticated sensors that are connected and monitored in a computer. And this is an outstanding idea, but to them it is rather expensive. So maybe for teachers who'd like to show the absolute zero measurement in a classroom, they could try, for an advanced level, they could try constructing this Arduino system. Okay, so what is this Arduino? If you guys are familiar, Arduino is like robotic basics. So there's like a kit that you can assemble. You can have parts put together, and then you can make a lot of things. So one of that is putting up an Arduino that senses temperature. So you can have these wires here, and then you can connect them all together in a breadboard, and then you can have a screen, and then the motherboard itself, that's the Arduino. We have different types of Arduino. Then you can program it. There's a special USB of that. You can connect it to the computer, and you can program, you can do the code, and then you can do a lot of things with it. So for this study, they use a thermistor. It's kind of a resistor that would be used to measure the temperature. So there's like a manual, and then they will choose a specific equation that they will plug in with the codes. So just to give you an overview of what the researchers could have done during the study. So yes, they embedded this thermistor in the breadboard, and then with the appropriate connection of wires, and then there's a code that you will encode here in the app to be installed together with the Arduino, and then you just plug in and save it in the flash drive, and then ibutang sa Arduino, and then it place. There's a special resource for this also. There's a lot katong Arduino. It's a Tinkercad Arduino. You can simulate this one. I didn't have the time to assemble. It's a Tinkercad, which is an online platform to make to test your Arduino. It's a good place, so try. So here, yung code and then connect. So this one. So it comes with a monitor. Your thermistor. Whenever you touch the thermistor, oh look, if you touch the thermistor, then it senses the temperature. And then you can also connect it with sophisticated other displays, such as this one, nga naay mga graph. So in this study, so here's the experimental setup, and they have this vessel, a metal vessel from a deodorant spray, and then they have this Arduino setup here, and then they use a stopper, and then a water tube, and then the sensor to be connected here. So they trap a gas here, and then we'll explain later how. So this one also, so in the metal vessel is opened and it shows the thermistor. So thermistor, it's here at the end. And then, so the temperature sensor, we have two types of sensor that they placed here. If you can remember, two types of sensor. There's one here, and there's another. So the first one, thermistor, it's the temperature sensor, specifically the 10 kilo ohm NTC MP52 thermistor. And then with the manuals that they use, the conversion equation of the thermistor resistance to temperature is based on this specific equation. So you can program different types of equations depending, because this one they're using a gas. Okay, and then for the next one, the next sensor is the pressure sensor. They didn't use an equation for the sensor, but they wanted to do it mechanically, and they used a 20 to 250 kilopascals absolute pressure sensor, or the MPX4250AP. And the pressure sensor is calibrated, measuring the signal as a function of the water column height. So it involves a water column. So this one here is connected to a water column. How it is measured is just like in this principle. So there's a special water column here, and then when there are changes, the pressure is detected. So if there's a greater change in height, that means a greater pressure, and a lower, when it lowers down, it would indicate a lower pressure, and the sensor would solve that with this built-in formula also embedded in the code for the sensor that they used. And it is then shown at the analog input of the Arduino, or there's this analog display screen, and then the plan is to measure this and graph it. So moving up and down one side of the tube relative to the other side, the water column generates a difference of pressure related to the heights between the meniscuses. So this one. So they use the Arduino to read directly the analog signal for different heights and build a graph to extract the linear relationship between pressure and the analog signal. So in their paper also, they provided with this schematic diagram or the sketch of the Arduino. So maybe if you could try to replicate it, then it's possible to do so. They also provided the source code that you can copy and paste. You can add it in the Arduino app already. So I think it's possible to do this. But in their experimental setup, this is how it goes. So the vessel is a metal vessel, so it can be at constant volume. So there's a stopper, and then the sensors are connected to an Arduino. I didn't draw the display screen and the breadboard. So inside, the gas is kept at 98.0 kilopascals and the temperature at 24.9 degrees Celsius. And then, so after that, they place it in equilibrium with a large beaker. And that large beaker they wanted to simulate it with a specific low temperature. They placed some ice, and then they placed cold water also. So until that system was placed into equilibrium, the cold water bath was 18.3 3 degrees Celsius. So they waited for equilibrium, and then they slowly heated it. So they placed what I call here heating something apparatus. So they heated it because I didn't see it, so I just draw my own. So I assumed something like this. So heating something apparatus, and at 0.5 kilopascal intervals, they heated it up at that interval until the water, the water bath, was heated to 61.8 degrees Celsius, assuming that it's in equilibrium with the material inside the vessel too. But it's just gas inside the vessel. But nakasaka po ang pressure because increasing temperature, increasing pressure. And then it was graphed and analyzed. And here are the results. So after they graphed it, they really have this linear relationship. So there's this linear behavior between the variables, the temperature and the pressure. So they only got around 68 degrees Celsius. So from the linear fit of these data points, we can extrapolate our results and we can find the temperature of the gas when the pressure is 0. So because there's a pattern, and so we can anticipate what is the temperature when the pressure is 0. The graph of temperature as a function of pressure showing the linear fit. The inset show the fit line prolonged to 0 pressure to show the temperature at this point. Okay, they want to do, if this is the actual data that they gathered, they want to zoom it up here and reach 0 pressure, 0 kilopascals. And what could the temperature be? So they tried to do that and solve it. So taking the intercept constant, they got this. It's negative 275, positive negative 4 degrees Celsius. So remembering that the Kelvin equivalent is 0 degrees Celsius or 0, or that is negative 273.5 degrees Celsius as agreed in international standards. So they got really close because it's 275, positive negative 4. So nasolve jud nila. So wow. Then what the conclusion? This experimental study, they had this experimental apparatus that uses Arduino with temperature and pressure sensors to study the gas thermometer. So by measuring the pressure of the gas at different temperatures, they were able to estimate the temperature at 0 pressure, absolute 0. We found that it's negative 275, positive negative 4 degrees Celsius for the temperature when the pressure approaches 0. So for them, when the pressure is 0, that is also one of the conditions when it is absolute, when a material is at absolute 0, because there are also many things that happen. So according to theoretical studies, at absolute 0, and that is when the enthalpy and the entropy also is at 0 at minimum, and also it's the motion is the least one. So though it is at thermodynamic processes, it is not reached yet, or theoretically not, but they were able to calculate it so with this sensor. So yes, it's a good study. It's a simple one, and I think high school level we can do this in the classroom. And if we could just study as teachers who study and teach them how to use Arduino, it would be a good experience for students also. Okay, so references from the paper, of them are professors, grad students, most of them, and this one. So there are a lot of them in the study. So done. Thanks for watching. And so here's my study again, and see you. Bye bye.